Here we go. Okay, this first one, if you got two tables, try and figure out which one's linear, which one's quadratic. Let's start breaking them down. How much changes each time. So -4 to -7, it's going down. It's getting smaller and smaller. So that changed by -3. And it looks like that is the pattern every time. Okay, it's changing by -3, but you gotta look at the other side. The other side is going up, and they're going up by 1 every time. Up 1, up 1, up 1, up 1. So this guy right here is the linear. But most importantly, the more you explain, the more points you're going to get. Linear because it changes at a constant rate. So what that means is every time it increases the same exact amount. Now that's the definition of a linear. This guy over here, 2 to a 7, went up 5. 7 to 14 went up 7. 14 to 23, and we're on to a pattern. Up 5, up 7, up 9. You can totally guess. Up 11, up 13, up 15. And over here it looks like same thing. It's going up 1 every time. So this guy is the quadratic right here. Okay, the quadratic because you're increasing at a changing rate. So your change is going up 2 every single time you add 5, then the next time you add 7, then the next time you add 9. So the quadratic because your second change is constant. So you had to break it down twice, and it's the second time that you found your constant rate of change. Okay, now the rules, the functions for both of these. The linear function is pretty easy. It's always going to be times by the change. So you found the -3 is your change. That's what you're going to times by. Now test a point. I'm going to test this guy right here, 4. I know 4 has to give me a -10. So I'm going to do 4 times by a -3. 4 times -3. Right now I'm at -12. How did I end up at -10? Then I think +2. So test one more to be sure. 2 times by a -3, that's a -6. -6 plus 2 is -4. Yep. My rule is going to be y equals a -3x plus 2. So those are not too bad. Now the quadratic, and I'll give you easy quadratics. Like for example, this one, I think this one's pretty easy. Quadratic, here's what you need to know. In your rule, you are going to have an x squared. There has to be an exponent of 2. So now if I just look at my, maybe jump down to like 4, look at 4. Okay, I know that when I plug something in, sooner or later I'm going to have to square it. So I'm going to try right now. 4 squared, that gives me a 16. How do I end up at 14? So maybe my rule is x squared minus 2. Let's try another one. You got to try a couple. Let's try 5. 5 squared is 25. Subtract 2 is 23. Yep, I think I got it. 3 squared is 9. Subtract 2. That puts me up at 7. Got it. So your quadratic, I'll give you an easy one just like that. Which pattern is quadratic? Which one's linear? Y. Write the function for both. Okay, these are a little different. Now, 8 to 12, that went up 4. 2 to 4, that went up 2. And you stare and sit and think for a while, but what I want you to write is not enough info for either of them. Whoops, not enough. Not enough info, because I know you added 4 here, but what is going to happen next? I don't know if you're going to add 4 again, or maybe you're going to add 20. I don't know what's going to happen. The pattern is just barely starting out. There's not enough of the pattern to figure out how much it's changing. All I know is it changed 4 times, and over here it changed 2 times, but I don't know what's gonna happen next. So for both of these, not enough info. You gotta have a minimum of 3 pairs, 3 pictures. Okay, let's see. Okay, draw a sequence of pictures that increases at a linear rate from picture to picture. So linear is x to the 1, and that is the first dimension. So don't need to be complicated at all. Picture 1, picture 2, picture 3, picture 4, and my change is +1 every time. So that's pretty easy. Now the next one, a quadratic. A quadratic is x squared, and that is the second dimension. So this linear one, that's kind of the father of all linears, and here's the father of all quadratics. Picture 1 is going to be that. Picture 2, picture 3, picture 4, kind of messy, but that's just 4 squared, that's 3 squared, that's 2 squared, that's 1 squared. So that's what they would look like. And the second dimension is changing in height and base, so it's changing 2 dimensions. Suppose you invested into something that increased your money monthly at a linear rate. Create a table to model this scenario. So on my table, this is the month, and this is the money. So month 1, month 2, month 3, month 4. Alright. So month 1, maybe I got $100. Month 2, I got $200. Month 3, I got $300. Month 4, I got $400. So it's easy. The change every month is +100. So that's a linear rate. Now same thing except for a quadratic rate. This is going to be month. This is going to be money. Let's do 1, 2, 3, 4. Month 1, maybe I got $100. Month 2, maybe I got $200. Now month 3, I'm probably gonna get $400. And then month 4, maybe I'm gonna get $700. And I'm gonna be kind of specific on this. Your change, there's got to be a pattern to it. So from right here, I went up 100. Right here, I went up 200. Right here I went up 300, so there is a pattern to it. The next one is going to be month 5. I'm going to get $1,200 because I'm going to go up $400. So as long as when I take your change, if I take it out the second time, this guy has got to be constant, the same thing. Okay, write the function. Alright, figure 1. Maybe you organize it into a table. That is a good move. I guess X and Y, but this is going to be cubes, and this is going to be picture. So picture 1 has how many cubes, and if you count them up, 2, 4, 6, 8, 10, 12. 1's going to give you 14 cubes. Picture 2 is going to give you 26. And picture 3, 1, 2, 3, 4, 42. Alright, now if you start looking at the change, this one went up 12. This one, 42 minus 26, went up 16. So I'm going to totally guess that the next one is going to go up 12 to 16. That went up 4 times. So I'm banking that this is going to be 20, because it's going to look like it's increasing by 4 every time. So the next one on picture 4, if I add 20 to 42, I'm going to get 62 cubes. So this would be a quadratic, because the second change is constant, but your pictures are changing in 2 dimensions. So the rule, the function, let's look at picture 3. Now here's what I see. It's kind of symmetrical. It's kind of, if I fold it across this line right here, they're going to match up right on top of each other. So I can just look at either one of them and times it by 2. But you do have to see that they're just copy and paste, that they're duplicates. So I'm going to look at this guy right here, and I'm going to try and find a 3 in that picture. So if I'm hunting for a 3, first of all, let's look at the dimensions. Let's look, I'm just looking at this rectangle right here, and I noticed that it is 5 by 4. And I'll go back to figure 2, and this is 4 by 3. And figure 1 is 3 by 2. Okay, I think I got it figured out. There's a pattern. If I jump to figure 87, that's the test. If you can jump around and you know what it's going to look like, I think you got it figured out. So figure 87, what is the dimension of the rectangle? So figure 3 is a 4 by 5. Figure 2 is a 3 by 4. Figure 1 is a 2 by 3. So I know figure 87 is going to be an 88 by an 89. And I know that because I just add 1. So 87 plus 1. And I added 2. This is 87 plus 2. Because 4 is just 3 plus 1. And 5 is 3 plus 2. So now, if I know that I'm just adding 1 to the height and adding 2 to the base, I can do my abstract pretty easy. For picture X, what does picture X look like? You're going to add 1 to the height, you're going to add 2 to the base, and then to find the number of cubes, you multiply those together. So it's going to be x plus 1 times x plus 2. That's going to be x squared plus 2x plus x plus 2. You got to do the distributive property, x times x, x squared, x times 2, 2x, but then I got to multiply both these by 1. Then add your common terms. So it's going to be x squared plus 3x plus 2. And I'm going to double that, because this gives you only that rectangle, but there's also going to be a duplicate right there. So I'm going to double everything, and I'm out of space, so I'm going to come way up to the top. If I double everything, I'm going to have 2x squared plus 6x's plus 4. And I have accounted for this rectangle and this rectangle. The only thing I need to add on are these little 2 cubes at the end. So I'm going to plus 2. So my function is going to be kind of a complex one. 2x squared plus 6x plus 6. but it's pretty slick to see with your eyeballs, because they just give you two rectangles. And I'll give you an easy one. Definitely not one harder than that. Okay, this one, maybe if you go with the table, figure 1 is going to give you 3 cubes, figure 2 is 5 cubes, figure 3 is 7, and you can probably guess figure 4 is going to give you 9. The change every time is up 2, up 2, up 2. So this is linear because your change is constant. So now I'm going to times by my change, and now we just have to finish the rule off. So let's test a point. If you're going to times by 2, let's test this pair right here. Let's test 2 and 5. So 2 times 2 gives me a 4. I need to end up at 5, so plus 1. So times by 2, then plus 1. So y equals 2x plus 1. Test it with 3. 2 times 3 is 6, plus 1 is 7. Done. Alright. Let's do some more tables. So 2 to an 8. That went up 6 times. 8 to 18 went up 10 times. 18 to 32. That went up 14 times. I think I got it figured out. This one's going to go up 18. So this is not linear. This is quadratic. Because you're increasing at an increasing rate. And that increasing rate is going up by 4 every time. Alright, now. You have to know what's going to be this. This second column means your exponent has to be a 2. So I'm going to give you an easy one. Let's see if this one's kind of an easy one. Let's look at maybe 3. Okay, 3. Let's see, what are we doing? If I take 3, if I start off and square it, 3 squared, I'm at 9. Somehow I need to end up at 18. And I know that 9 is, if I double it, that's 18. So that's maybe a coincidence. Let's check one more. Let's look at 4. Okay, 4. If I do 4 squared, that puts me at 16. But I need to end up at 32. And I know that 16 is half of 32, so I don't think it's a coincidence. I think that's legit. Let's try one more to be sure. 5. 5 squared is 25. 25 doubled is 50. So here's my rule. I'm going to square it and then times by 2. So I'm going to double it. Square it first and then double it. Okay, this guy right here looks like they're going up. This is going up 1. That's going up 1. That's going up 1. Now these go up 1 as these go up 4. So this is a tricky question. How much is it changing every single time? All I know is the change of every 4th time. Every 4th time it changes once. So how much does it change every single time? So you gotta think of it this way. You just made $1 for 4 hours of work. So you're only making 25 cents an hour. You always do your y's divided by your x's. So it's going to be 1 divided by 4. So my change is a 4th. Every single time it's going up a 4th. So I'm going to times by 1/4. And that's the same as dividing by 4. So let's try 28. What is 28 divided by 4? That's 7. But I need to end up, 28 gives me a 4. So right now I'm at 7. So times by a 4th and then minus 3. So I think that's it. Let's try one more. Let's try 20. What is 20 times by a 4th? Or what's 20 divided by 4? That's 5. What's 5 minus 3? 2. So I got it. Y equals x divided by 4 minus 3. Okay, these guys from your first test, problem number 1, you're going to add the exponents. So it's going to be x to the 1/3 plus negative 3/8. Because you're multiplying two powers, add the exponents. Now this is a 6th grade problem. Adding fractions, you have to have a common denominator. So I'm going to change them both to 24ths. So how many 24ths is 1/3? That's 8 24ths. How many 24ths is negative 3/8? If I times them both by 3, I'm at negative 9. So I am x to the negative 1 24th. Now, that's illegal. Cannot have a negative exponent. So, move number 4, I'm going to write it as 1 over x to the 24th. It's still illegal because you can't have... No, see, that's not right. It's 1 over x. It's not x to the 24th. It's 1 over x to the 1/24th. Okay, that's illegal because you can't have a rational exponent. So you are going to multiply this by 1. And at the end of the day, I want to end up with x to the 1 whole power. So x to the 1. So right now I got x to the 1/24th. I know I'm going to do x to the 1/24th plus something equals x to the 1. So the question is, 1/24th plus what is a 1? And the answer is 23 24ths. So I've got to multiply both the top and the bottom by x to the 23 24ths. Because 23 24ths plus 1/24th is actually 24 24ths, which is the same thing as x to the 1. Okay, now when I times my tops, when I times 1 by x to the 23 24ths, I just get x to the 23 24ths. When I times my bottoms, I get x to the 1. And that is your final answer. Okay, anytime you've got underneath the radical a pretty large number, let's do its prime factor. So 625, I'm going to divide it by 5. 5 times 125. Now I'm going to break up 125. 5 and 25. Break up 25 is 5 and 5. So instead of a 625, I'm going to see it as its prime factors. So I'm looking at this. I'm looking at the 8th root of 5 to the 4th. And now if you morph it, it's going to be this. It's going to be 5 to the 4/8. And you know 4/8 is the same thing as 5 to the 1/2. And you know that that is the same thing as 5 to the 1/2. Square root of 5. So we want you at the end of the day to end up at square root of 5. Because they give it to you in radical, so maybe your answer looks best as a radical. If you end up this far, that's still full credit. Next one. 4th root of 8 times the cube root of 16. So your golden rule, anytime you've got a number underneath a radical, let's prime factor it. Always, always. It's going to be 4 times 2, that's going to be 2 times 2, so you're going to look at this. You're going to look at 4th root of 2 cubed. Now 16 is a 4 and a 4, a 2 and a 2, a 2 and a 2. So cube root of 2 to the 4th. Okay, now if you morph these guys, you're going to have something a little more appealing. 2 to the 3/4 times 2 to the 4/3. Okay, now what's awesome is my base is the same. So if your base is the same and you're multiplying two powers, you just add the exponents. So here we go. 2 to the 3/4 plus 4/3. Fourths and thirds, change them both to 12ths probably. Alright, how many 12ths is 3/4? 9 12ths and 16 12ths. So you're going to have 2 to the 25 12ths. And probably just because my problem started out in radical, I'm going to express the answer in radical form. So let's morph it. Let's go 2, the 12 goes here, and the 25 goes here. Now the 12th root of 2 to the 25th, you can pull out sets of 12. How many sets of 12 do you have in 25? So you can pull out 2 sets of 12, and you are going to have 2 sets of 12 is 24, so you're going to have 1 left over. So 2 squared, 4 times the 12th root of 2 is the very best answer. Okay. Let's see. How much do we have left? I might have to split this up into 2 parts. Yeah, let's maybe call it good right here. And I'll do a part 2.